Hey guys, today we're going to do the AtCoder beginner contest 176, and yeah, before we start I'm going to add in the new subscribers and the new bits. I'm pretty sure this number is inaccurate, but I mean there's nothing we can do. I'm using the analytics because eventually we go to other channels, that's going to truncate the public subscriber count, and I don't want to do that. So we'll just have the exact number, and on the topic of that, even though we haven't hit a milestone, I just want to say, thank you guys for being here. It's been really fun doing these screencasts, and the crazy support I've gotten makes it even better. So, yeah, slightly sentimental here. Just thank you guys. Anyway, here we're doing another one. Starts in 10 seconds. So let's get into it. Taking team. Okay, so we'll just use generic variable names. Then it's basically the ceiling of n over x times t, because that's the number of batches we need to make. So the ceiling would be x plus y minus 1, floor divided by y, and then multiply all of that by c, because that's what we need. That's how much time it takes for each batch. Okay, this one we just straight up do the sum of digits. We can subtract the digit 0, that will give us everything. Then if this is not 0, then no, else yes. And that just does exactly what the problem tells us to do. Print yes. Print no. And yeah. Okay. Condition: nobody in front of the person is taller than the person. Okay, so if we go backwards, then it's strictly better to use as few stool spaces as possible. So, we're basically just going to worst equals. So worst is we're gonna go backwards and keep track of the highest value before. Then, if the highest value is greater, then we need to increase the one we're at right now. So for minus, if AI is less than worst, ants plus equals worst minus AI equals worst. worst equals max worst AI. So again, we're going backwards and basically keeping a prefix maximum, and that will do everything we need. Or not. Wait, what? Nobody in front of the... Oh, okay. So we just go forwards instead. 0. Okay, that's kind of confusing notation. Then I++. Okay, what now? Why? If AI is less than worst. Oh, wait. I is less than n. Copy paste errors are bad. Yeah. Okay, now we get 4, and here 0. Maze is composed of a grid. There's a magician. Okay. So this is 0, 1 BFS, where normal BFS would keep a queue where, like, let's say we're at 3, for example, and these are all the locations with cost 3. So we would keep a queue like this with all the 3s, and then if we have something with cost 3 plus 1, so the key here is that we only have edges with weight 0 and weight 1. So we want to find the shortest path from some vertex to another vertex. So everything with 3 we'll put in the front because we might as well, and everything else with 4 we'll put in the back. And that way, just like BFS, we still visit things all in increasing order, and we only have 2 different types of elements at most in the queue. Because 3s are only going to add 4s to the back, and you'll only start getting 5s once you move on to the 4s, and therefore get rid of all the 3s. And then you continue on. That's a very brief description of 0 and BFS. I'll give you a better one later once I implement this. So, okay. So Cn to N to M. Cool math 2005. I'll just use these for the coordinates. These are rows. Yes, ith row from the top, jth column from the left. Okay, so what are we gonna do? What are we doing? See into the string. Okay, sorry, I got a bit distracted there by nothing. You ever have that happen to you? Just like totally lose your train of thought. Ij equals sj equals. So we're going to convert the whole thing to booleans, and where it's going to be true if it's not blocked off. Then bool this. Wait, does that work? Let's make a pair of. So it's going to be a pair of the position and then the cost to get here. Wait, this should be a deck. We'll call it Q anyway because I'm lazy. Now, q dot push make pair a b, and then 0. Pair x equals q dot front, q dot pop front. Now, if this x dot first, x dot second, continue because we don't want to revisit things, then this x dot first, x dot second. We can do this because, again, with 0, 1 BFS, we're guaranteeing that we visit every place at the fastest time we can get there. Now, bool dr4, standard stuff for traversing grids, just like a dx and dy array. R is greater than 0, R is less than n, C is greater than or equal to 0, C is less than M. That means it's within the grid. Now, NR equals, oh wait. Grid problems are always annoying to implement. Plus drd, and C equals the old position plus wherever we go. If valid, NR and C, and it's not blocked. I guess not visited, NR and C, just to make it nicer. Q dot push front, make pair, another make pair, NR and C, and this is the same cost as what we have now because it doesn't take any magic to do this. And now we're going to go through the ones that have magic. So for so in the 5x5 square means that it can go at most distance 2 away. I'm not going to draw the square right now, but like here that we have this, then we're 2 squares away. So we can go anywhere from -2, -2 to +2, +2, and we're just going to traverse all of these. And we'll copy this. So now we push it to the back because 0, 1 BFS, and this will be x dot s plus 1. If pos.f equals c, pos.s equals d, c out x.s, because we're done, we just found the answer. Then otherwise, I guess c out -1. Is that what they want? Yeah, print -1. Okay, let's do this. Compiling. Comma. Why did I do that? What? What exactly are we doing here? What did we just do? What did I screw up here? Okay, why? What am I printing? What have I done? Oh, it didn't even, okay, it didn't even compile. I see, okay. Sorry, push front, or actually it doesn't matter. Alright, I'm stupid. Yeah, not even noticing that it didn't compile. That is a good thing to pay attention to. Cool. Why does that happen? Bruh. Still. Why? Okay. Alright, let's see, just print where we're at. Right. 0 indexing. Okay. We get 1. -1. 0. 2. Okay. Let's do this. Let's make sure we did everything right. Constraints are good. We wrote valid. Okay. That's clarification. Or not. What? How do I make these booleans? Also, wait, did I not catch that? Did my compiler still didn't catch that? That is weird. Is that the only issue? Yeah, the rest are just warnings. Okay. Good. Another what? Another two-dimensional grid, except this one's bigger. Okay. And there are M targets. The position is that. Bomb will destroy all targets that are in the row or the column where the bomb is placed. It is possible to place the bomb at a square with a target. Okay, this one's relatively easy. So we fix the row that we put it in since there aren't that many, and then we just find the column with the maximum value. Yeah, okay. So let's say we have some, just give a brief idea. So let's say we have some stuff here, and then we have some stuff here. All right, so we'll keep track of, like, we have 1 in this column, 2 in this column, 4 here, and then 1 here. Then let's say we get rid of these rows. We update these counts based on what's in the row, and then we just take the maximum over the column to put it in, and then we'll add that to the number we just deleted in the row, and that'll be good. That's my plan. I don't think it will fail, so I hope it doesn't fail. Okay, so C into N to M, then what is this? Not able to understand the meaning of okay. C into N to M, and then we're just gonna call it K because I'm totally screwing with the variable names here. Now, so vector LL in row, then we'll make it huge, 300,005, and C into X, Y in row Okay, now we're going to, okay, 3 seconds, good. So we're going to keep a multiset of all the lengths we have, that way we can easily extract the easiest one. Then, best map long, and we're also going to use a map to, actually no, we don't need a map. LL, x.push back. And we use C to represent the count in each row. For I equals 1, I is less than or equal to M. I'm using 1 indexing here because I'm weird. Actually, no, that's definitely going to bite me in the back later, so let's just not do that. We're going to make it 0 indexing again, and just start things from 0. Then CI equals 0. Void update allow position and allow the change delta. Then best.race, best.find, C pause, C pause plus equals delta, then best.insert C pause. That way we're just updating it both in the multiset and the count itself. Upt y negative 1. Is there another one? Okay. So I is less than n, I plus plus. It's 0. Allow cur equals, we're just going to start off with the number of things in our row, I.size. Then for each value in row I, delete it. Then if best.size, take the maximum, best.rBegin, which works as the maximum. It's the reverse beginning, which is the end element. Then we're going to put these back in. And that should be it. Or not. Did it not compile again? What are we doing? So we have 2, 3, and 3. What exactly are we doing here? Oh wait, because we need to insert that. Yes, we can erase elements that don't exist. That is a good idea not to do. So we can get all 3. We get 3. We get 6. Okay, let's just check again, make sure. CI equals 0, best.insert 0. Each thing in row x dot push back y. Even though we actually inverted x and y because it's rows and columns, but whatever. That's equals 0. So first take all the things in the row, then remove them, then take the maximum of all columns, then add them back. And here we're going to erase the previous value and then put in the new one, and that's it. Okay, I trust it. Wow, that's a lot of tests. Why do they have so many tests? Wow. Okay, let's just read this. Okay, we have 3n cards arranged in a row. Every card has an integer between 1 and n. There are just so many tests here. Inclusive written on it. The integer written on the ith card from the left is AI. I just want to see the satisfying, like, AC times 130, because there's so many. Actually, there are 133 with the samples. Okay. Anyway, whatever. Doing fine right now, I hope. Yeah, not bad. Okay, so let's continue. We have one problem left. Do the following operation n minus 1 times. Rearrange the 5 leftmost cards, then remove the 3 leftmost. If the integers written on those 3 cards are all equal, you gain 1 point. So if we remove 5, right? Then say we decide to keep, like, these two, for example, and we move them to the end, so we have, like, let's say we have 1, 1, 3, 2, 2. Then we're gonna move the first 3. But, like, these are now in the beginning. So whichever 2 we choose to keep, we're never gonna move them out of our reach. They're always gonna stay within our reach. I don't know if that helps. So the way it works is our initial 5 is our initial 5. Then we choose 2 to keep. Then we take 3 more. So let's say we have 1, 1, 2, 2, 3, 3, 3, 2, 1. So the way this works is we're gonna take 2 out of these. Let's, for example, say we keep 1 and 2. Then we're gonna remove the rest. So now our new sequence is 1, 2, 3, 3, 2, 1. So now these 2 still stay within our 5, and now we just pick up 3 more new cards. And then we pick whatever 2 we want from here. Let's say we remove these, then we get 1, 2, 1. So at each stage we only get 3 more new cards. And so what? So what indeed? So if n was smaller, we can do a sort of dynamic programming where we're focusing on the position than the 2 cards we previously took. But n is too large for that, so we can't. What can we do instead? Let's say we've gotten to some place and kind of weird how in the samples there are always 3 of each card, but I don't know if that's guaranteed. I don't think so, because it doesn't specifically say that. So if we can make a match, should we? So it's like we gain these 3, and we get these 3. Um, remove these at least, because this isn't necessary anymore. And so we have some weird case like, let's say like 3, 3, 3, 2, 2, then 3, 3, 3, 3, 1, 3, 3, 1, then 4. So if we make this match, then we're going to end up with this batch. Oh, we can make those 3s work. Okay. Good. So an element we take is either going to be useless or we're going to use it in a match later on, let's say. Okay, does that help? Not sure if greedy is going to work. Let's say we have some scenario where like 3, 3, 1, 1, 2. So 2 is useless. Then, let's say we have like another 2, then I don't know, 4, then a 3, and then 4, and then a 1, and then a 1, and then a 5, and then a 1, and a 1, and then a 5. So these are the groups we're gaining each time. So 2s, 4s, and 5s are all useless, therefore we only care about 3s and 1s. And so even though we get a match with 3s earlier, we want to take the 1s because it'll make it better for us long term. Wait, no. That's not necessary because I keep thinking this, but we can take these ones later on and then use them to make a match with these ones. Okay. So maybe greedy does work. Greedy as in greedily take the ones that will let us make a match in the least amount of time. Would that ever fail? Just the case I just thought of doesn't fail because we can take things later on. Like, it only fails if it's possible for it to be better to take one that will help us later on rather than early on. But when would it be helpful to take one that will help us later on? Indeed, when would that be helpful? Let's say we had a filler here, like 5, 5, 5. So we'll obviously just take that match. Then let's make this 4, 4, 4. Wait, no. Oh, you can make one of these 2 and then they'll be useless. What? What are we doing here? I don't know what I'm doing here. So we want to make it so like, I don't know, 3, 3, 1, 2, 4. Then we'll get like 5, 5, 3. Then we'll make 4 useless. So 4, 1, 1. And then like something 2, 2, and then something. That's what we want. So we had for example 6, 2, 2. So this would be like this, like this, like this, and like this. We'll just add a bunch of 6s. So initially, these 3s would let us get a match with this one. However, if we took the 1 and 2 instead, then we'll be able to get a match here and here. Which is, I think, better. And we'll get a match of 6s anyway. So that may disprove things. What do we do then? What's this? Okay, not necessarily. That just happens to be in the samples. Okay, so the integers are all equal. Right, so that won't work. So if we were to do some sort of dynamic programming, it would have to be necessary to store, first of all, the position, since it's like where we're at. And then second will be the numbers we have. I'm not sure what else to do. Either we reduce the state space or try something else. I guess something else notable is that the number of points is at most n as well, because we can get at most 1 point each round. Does that help at all? Why would it? Maybe something else that's interesting. If we have like let's define just our state as the 2 cards we have and the points we have so far. Like, let's say we have some. That corner case is useless. Let's say we have some state with like, I don't know, 77 points, and then like 3 and then 5 is our cards. Then like any state with like anything less than or equal to 74, for example, and let's say we have better cards, cards that will show up in the future. Even if we have better cards, it doesn't matter, because these cards are going to let us make at most 2 matches, and these cards are going to let us make at most 2 matches. However, we're already 3 matches ahead on this one, so we don't care about being here. I'm not sure if that's helpful in any way. I don't know. Let's see, is this hard or are we just missing something? Oh, wow. Okay, this is not easy then. Alright, we'll still keep looking, of course, but I guess it's not necessarily easy. Okay, what if we screw with our state a bit? So let's completely drop the position. Then so we can find out for, like, let's say we have two cards. We can find out exactly when they'll be necessary to make a match. Necessary meaning, like, say we have 2, 3 right now. Then, like, if we get like 2, 2, 2 as a later set of cards, then this 2 isn't necessary. So let's say when are we allowed to get rid of the 2 and then take something else? Because either we have the 2 for our use, or we're just having it because we need to have it, and the same for the, or we're just having it because, like, we don't have, there's nothing better to store, for example. So so the state I'm proposing is it will be answer and then first match, which stores the second match. Okay, now it's important that the answer is at most n, and by first match and second match, I mean the time, like the earliest group of 3 cards in which we're going to use this for a match. We also include the first match as part of our state because, like, okay, that's a coffee maker, not a smoke alarm. We include that as part of our state because, like, we don't know. Like, let's say we have a first match that's going to happen at 3, and a second match that's going to happen at 7, and a first match that's going to happen at 4, and a second that's going to happen at 6. Like, we don't know which of these is going to be better in the future. So we'll just, like, also fix, like, whatever this is, say star and then 3, which stores 7, and then star, and then, it's not a star, that's a line, star, and then 4, which says 6, and that's how we're going to represent that. Now, does this work, and how do we compute it? Here's another question. First of all, does it work? If we fix both the time of the first match and the second match, then, or if we fix the time of the first match, is it ever like not good to store the time of the second? Wait, what? Doesn't make sense. Do I have those edge cases, or do I not? Or okay. So will this work? And if so, why does it work? That is it ever better to have a later second match? I don't think it would be. Because if, like, a second match is worth at most 1. So no matter what happens, like, there's no better second match that comes later because each second match is worth the same amount. So I think that does work. And the answer is at most n. So let's do this. LDP, let's say 2005, and C into n. Now what? I'm going to pad the array with zeros. Could be convenient. So now note that it does not matter which elements we take. Yeah. So let's say we have two of the same cards, like the two things we have is 3, 3. Then we're gonna make a match with, for example, 2, 2, 3 in the future. Then there is no second match because all of these are going to be used to make the same match. I guess in that case, the second match will be infinity. Let's see. Only 7, doesn't matter how big it is, really. Then we'll make the second match infinity, and then we'll, I guess, use that. Okay, let's do some auxiliary stuff. Like we're gonna say we have an array that says next pause or next value, or maybe next position how do we do that? Next position value start. That basically says when we have, so either we'll have 1 or 2. Either we'll have 1 or 2 of these. And basically asking, when can we like make a match with these? Let's say we have, for example, we're at position 3. We have two 4s, and we have 2 4s. Then we're asking, when do we get exactly one more 4? Okay, perhaps not exactly one more action. Let's say, when do we make another match using what we have? So it's interesting. Like, let's say we have this case, like 1 1 2 2 2 3 3 3 1. We kind of want to just ignore these. Like, these we're gonna get matches with no matter what. So that's kind of interesting. I think that's kind of what we want. So for LL I equals 0, I is less than n. For LL L we're also, for implementation, we're sticking 2 zeros at the end of the array. That way we can just be convenient about this. Okay, now let's just what exactly do we do here? Also, more people solve this. Okay, this is very not easy. So, once we compute next, then what? What can we do with that? Once we compute next, somehow we have to use it to help us in computing DP. Not really sure how. Well, we also have like, say if it's even possible to have this value, or have at this position this value. So like, if it's even possible to have an answer. Wait, no, that's not necessary. It would just be possible here, I guess. Then we'll update it as we go. Is it even possible to do the transitions with this? I don't know, I very much would not like to implement this, so maybe there's a better, like, easier thing we can do. And I hope there is. I really do hope there is. It's like in 20 minutes, 3 more people have solved this. Which is crazy. What kind of errors are people getting? I'm interested in seeing that. Guess we'll see after. So I'm not even sure if this works, because like maybe the transitions take too long. How do we even do a transition? Well, we're at a position. We're at some position, then we put another. We take another few cards, and well, technically it's only the states. And wait, now that's not necessarily true. What I was about to say was that it'd be only the states where the first match is equal to the position we're at, but that's not true, because we could take some different card that will like improve our second match later. So maybe that's not good. The idea would be to go through positions and then see how like taking another like iterate through each position. Then if we take some number of cards here, or if we make a match here, like how does that affect our state? Does it make it better, or does it give us a better answer, or what? Although I don't think that would work, because I think in the worst case we would have to visit all the states every time, and that's also n cubed, which will not work. They made it very clear that n cubed is not supposed to pass with n equals 2000. So let's not do n cubed. So somehow we have to optimize out something else. Okay, I'm actually glad that doesn't work, because that would be a very big pain to implement. Because you'd have to like compute next, and then you'd have to like do a whole bunch of casework on what your first and second match is. And I think you would also have to maybe brute force the next pair you take. I don't even know. It's very messy. And I don't like it. So that's good. And it might actually not even work because there are a lot of reasons why that would be messy and it's very easy to screw up. So I'm not sure about that solution. So I'll keep it on the screen for now since I have nothing better, but I guess we'll keep thinking. How far are other people getting with this? Seems like most of the mistakes are on the last problem, which is annoying. Okay, anyway. Entries written in those 3 cards are all equal. You gain 1 point. So nice one operations. Yeah. Why am I rereading the problem? I don't know. One thing that's still interesting is that we only care about answers that are within 3 of our best answer. So maybe that helps somehow. Or like, we only care about states that have answer, answer minus 1, and answer minus 2. Wait, is it even answer minus 2? I don't think it is, because the best we can get... Oh, wait, no. Wait. I'm not sure, because if we have a state with answer minus 2, then it's like strictly... Or it's just as good to have a state with answer, because... like even if the 2 cards we have right now are useless, and the 2 cards we have in the state with answer minus 2 will be used, then like will only be just as good as the state with answer, and therefore there's no reason to keep track of that. Huh. That's kind of interesting. So either we have the best answer or we have not the best answer. We have the best answer or we have the best answer minus 1 at some position. So that's useful. How useful is it? Are we able to use it somehow? And if so, how? So if we have the answer, then we can store whatever we want. And if we have answer minus 1, then I'm not sure. We have the answer minus 1, then it may be necessary to store two that are different, because that's the only way we can get an advantage over answer later on. Maybe that's true. Don't exactly know. So we can cut down the state space, but then like what do we do with that reduction? We have to make it easier for ourselves somehow. So maybe we can do this. DP on the answer and the position of the first match, then we store the best position in the second match, because we only have two answers to keep track of. Yeah, that's the thing, we only have two answers to keep track of. But like, is there a less annoying way than storing this information? I really hope there is, because I still don't exactly know how to implement this. Like, the case that makes this kind of implementation difficult would be something like, where we have like 2-1, for example, and then like the first match requires us to get rid of this 1, store another 2, and then we have some other thing with like XX and 2 that we need both of these 2s to make a match for. Because then the second match wouldn't actually exist, which is a problem. And is annoying. And the second match wouldn't actually exist. So what do we do in that case? What do we do in any case? We might as well store position in the state since it doesn't really matter. What if we just stored like the first card? Like position, answer, and then first card. And then either the second card is equal or it isn't. Then does that make it easier? Like it's also not necessary to include in the state, maybe. Maybe we don't need to include answer in the state at all. But then that makes it harder. Doing some like heuristics wouldn't work because it'd be easy to make a case where all of the answers are 0 up to a certain point. Like just do 1, 2, 3, 4, 5 up to n, then another 1, 2, 3, 4, 5 up to n, and so on. I'm sure they have that case because these AtCoder guys are kind of smart. So I'm not going to trick them that way. Well, I guess we continue the curse unless we can do this in 13 minutes. Maybe the implementation is simple and it's just the idea we have to get. That'd be nice if it was. I mean, last ABC we did, the implementation was almost harder than the idea. How are we doing right now? Any last-ditch efforts we need? I mean, it is a hard problem. Wow, this guy won the last one too, didn't he? What the hell? This is like some secret LGM or something? It's kind of crazy to win 2 ABCs in a row. I mean, he's not exactly competing with other LGMs, I wouldn't say. Maybe, actually. I don't know who's doing this, but still, that is kind of crazy. Anyway, I'm just going to pace around some more, see if we can get any other ideas, I guess. It'd be funny if we got the same rank as last time. Same rank as last time where we struggled the whole contest on F, but this time we put like 20 minutes of effort in and just solved till E. I guess that's how speed works. Anything interesting to store about the second match? Maybe? Like first and second match are hard to define because the state, I guess it could change over time. Well, no, that doesn't matter. But seems like kind of hard to think about this kind of thing because we have to quote unquote look into the future to see when our next match is going to happen. But at the same time, like our state could change in the future. I think it's definitely true that having the earliest possible one would be best, but even just the idea of a second match is hard to define because it may be optimal for us to get rid of our second card, delete the second match in the future, and yeah, because the acquisition of our first match may depend on getting rid of the idea of a second match, but we still have to store a second match for it, which is kind of weird. And of course, to do all this, we have to compute the next array, which I think is some very weird two pointers thing that we have to do. I don't like that at all. Well, actually, it will be 2 pointers for each possible number. Luckily, they're only up to n, but it will be 2 pointers for each possible number. I very much don't like that. Okay. Well, with no ideas, we'll call it quits in 1 minute, because I honestly have no idea what to do. Sad, you blitz through everything, but get nowhere. Very much not sure where to go here. We have this just unwritten code. How are we doing? Do we have a full set of 20 people who saw this yet? No. Wow. Wow. Crazy. Huh. And most people who end up solving this have a worse penalty than I do, so they shoot above me later on. That kind of sucks. That would be very funny if we actually end up with the same rank. This is a friend system. I have to, like, friend people. The people I do have friended don't do anything. Okay. Well, that's the best we can do. Kind of hoping for rank 55 again. That would be very funny. Because we did everything in 23 minutes, and then we basically did nothing else. We'll get the same rank. I also realize that, like I do spend extra time to sometimes make sure that what I'm thinking is clear as I implement it, and that does slow me down a bit, but I mean, I don't really care. Like, this is all for fun anyway. So maybe let's see, this was definitely based on speed. Like, a few seconds would have gotten me a higher place, but like, it's not that big a deal, really. Jesus, 12 minutes. That's crazy. You just how do you implement all that grid stuff in 12 and what was it even? This was 5 minutes to do all the grid stuff. Crazy. I'm just slow on grids, actually. That's part of my problem. And it gave me trouble. Anyway, this contest being meant for beginners, I don't really have the ability to judge it. But most of these, relatively standard, but I guess that's fine. Check one more time. And then we'll start going over solutions. Okay, yeah, rank is barely going to change. So let's go over everything. I'm just not going to try explaining F because I don't have any ideas for it, honestly. So we'll just do this. Okay, let's do A. A is takoyaki. That's how you say that, right? So you have a bunch of pieces of takoyaki. Let's say you have 20. Is that what the sample is? Yeah, so let's say you have 20 of these. I'm not going to draw 20 of it. Let's say you have 20, right? So you can pick some batch of these takoyaki. Like, for example, you can pick some X, or you can pick some like C, where C is between 1 and X, and then you can take T minutes to, what is it, to make C pieces of, is it pieces? Yeah, okay, I very much don't know the terminology here. So it'll take 2 minutes to make C pieces of takoyaki, and you can make at most X. So you want to find out how long is it going to take to make exactly N, in this case is 20. So first of all, like it's not going to hurt you if you make more. So at each step, you might as well make as many as possible. So on the first step, you're going to have X. On the second step, you're going to have 2X. On the third step, you're going to have a disgusting 3X, which I can't even undo. Okay. 2X, 3X, etc. And you want to find out what's the lowest, let's say K, such that Kx is greater than or equal to N. And the time it takes is K times T. So you want to find the value of K times T for the largest K such that, or the minimum K such that Kx is greater than N. So all the constraints are small, so you could, let's check my final rank. All the constraints are small, so you could, I beat my old rank with 23 minutes of effort. What the hell? Okay. So these constraints are small, so you can just brute force the value of K, and then whenever Kx is greater than N, you'll be done. So that will be O of N, I guess. However, there's an easier solution. The lowest integer such that Kx is greater than N is the definition of the ceiling of N over X. That is, you divide N by X and round up. So, yeah, I mean, that's just the definition. So the answer is either you brute force it or you just take the ceiling of N over X times T. And the way to do ceiling is, so like in many languages like C++, basic division is floor division, which means like it would be floor of 7 over 3, which is 7 over 3 rounded down, equals 2 plus 1/3, wait, floor of 2 plus 1/3, and then you round down, so it's just 2. So the way to do it in floor division is, because we have integers, we can basically make it as the floor of N plus X minus 1 over X times T. Now that's a nice way to implement it, and the reason this works is because, like, first of all, So either n is divisible by x or it isn't. If x divides n, that's the terminology, then this isn't going to increase. Because if x divides n, first of all, then the floor of n over x is equal, the ceiling of n over x is equal to the floor of n over x, because n over x is an integer. And so if n divides x, this isn't going to, or if x divides n, this isn't going to change. And otherwise, like, it's, you can work out why it doesn't change. It's just like the math. And otherwise, n over x, ceiling n over x, is equal to floor n over x plus 1. So in any other case, this is going to change. It's going to change, like adding x minus 1 is going to increase it by 1 in all other cases. So therefore, the formula just works. That's basically what I'm saying. If you don't understand my explanation, you can just, I guess, try and work it out on your own on paper. It's kind of intuitive, kind of not. Anyway, so that's it. It's just t times the ceiling of n over x overall. Wait, I think my placement might change. Okay, so an integer n. Alright, okay. So this one you just check, like, if a string is a multiple of 9. And they say an integer is a multiple of 9 if the sum of the digits is a multiple of 9. So you're given the digits, like 2, 3, 4, 7, right? And you want to check if the sum of the digits is a multiple of 9. So first, just take the sum of the digits. Plus 7 equals 16. You can do that with a loop, I guess. And then check if the sum mod 9 is equal to 0, but it's not. In this case, it's equal to 7. So it's not divisible by 9. However, let's say we had 2, then you'd make that an 8, make that an 8, and then this would be 0, so it will work. So you would literally just take the sum of the digits and check if it's multiple of 9, and you do that by taking a mod 9 and seeing if that's 0. An easy way to get the value of a character is to do like string at value I minus the character 0, and that way 0 will map to 0. Like 9 subtracted from 0 is mapping to 9, and etc. It works for all characters. I think that will work in C++. I don't know about Java. In Python, you have to do like, I think it's ORD 0, and like ORD stir I. Anyway, it's not that big a deal. You can implement it however you want, but the basic idea is you want to get the value of each character, sum them, check if they're a multiple of 9. Like, just do exactly what it tells you to do, honestly. 51. Pretty good. Better than last time. Just kind of sad. So I remember last time we had like a 50-minute long struggle to get F, and we did, and this time we didn't even get the idea. Okay, so here, at least this isn't, like there's some thinking involved in this one, kind of. Some, but not much, but some. So you're given an array, and in one operation, you can increase any element by 1. Let's say we do that, then we do that, then we do that. And you want to make it so for every element, there's no element that comes before it that's greater than it. Okay. And so what's the minimum number of operations to make this true? So basically we want to sort the array. Well, we don't want to sort the array. We want to make it so the array is sorted. So for example, 2, 4, 5, 7, 9 would work because you can do 3 operations here, 3 operations here, and 6 operations here, and you don't decrease anything. However, 2, 2, 5, 5, 5 also works. So the general idea is, obviously you want to make as few increases as possible. So if we increase this element, let's say to 6, then we're also going to increase everything after it possibly more times. Like say we increase this element to 5, then we have to increase this element twice. But if we increase this element to 6, then we have to increase this element 3 times, which does more operations on both of these. So now we know that we want to increase each individual element as few times as possible. So let's use the exact wording of the statement. We want it so there's no element behind or in front. Okay, there's no element that comes before this element that's greater than it. So that means we can reformulate it as the maximum of the elements that come before it must be less than or equal to this. So now we just need to find the maximum of the elements that come before it and then increase this to that maximum. So how do we do that? Well, we can keep a running maximum. So let's say let's like do some. So we're gonna sweep through the array in this direction. Then let's say this. We're gonna keep track of the maximum we have so far. So the maximum of these elements is obviously like anything that's less than all of them. So this is 0 in this case. So now we're at 2. 2 is greater than 2 is not less than the maximum, so we're fine. We can keep it as it is. But now the maximum element is 2. So now we're at 1. 1 is less than the maximum. So we have to increase it to the maximum, which is in this case 2. Then the maximum of 2 and 2 is 2. Now 5 is greater than the maximum, so we're fine. And now the maximum is 5. Then 4 is less than the maximum, so we have to increase it to the maximum, which is 5. Now the maximum is still 5. Then 3 is less than the maximum, so we have to increase it to 5, and so we do. So we use one operation here, and 2 operations here, so we do 4 in total. And that's basically the idea. We keep a running maximum of the we go through the array in this direction, then we keep a running maximum of the elements we've seen before. Then we just check in the current position if we need to increase it, and if so, we increase it to the current maximum. So that's the process we do. You can think of it as it's like prefix sums with maximums. You can call them like prefix maximums or whatever. If you don't know what prefix sums are, learn those. They're useful. So let's go to D. And okay, now we get to. So the first 3 problems, they were simple. At least they were harmless. This is at least there's no edge cases, but this is like an annoying problem. So we have a grid. Bang, bing. I'm gonna draw out a sample. Okay, certain cells are blocked. I'm gonna color them in red. So this cell's blocked, this cell's blocked, this cell's blocked, and this cell's blocked. Now so we start a cell, let's say the blue cell, and we're trying to get to the green cell. Yeah, that's a sample. So there are 2 things you can do. You can walk to any cell that shares a side with your cell. That is, you can go up, left, down, or right. And you can use magic to teleport to any cell that's within the 5x5 square that's centered at your position. So for example, if I drew this square, then we could teleport to any cell here. Okay, and each teleportation costs let's say it costs 1 coin, and we're trying to pay the minimum amount of coins, or I guess each teleportation will use your magic, and you want to use magic as few times as possible. So you want to do as few teleportations as possible. Okay, now first of all, let's make it a bit easier. So teleporting to any cell within the 5x5 square means that like think about the distance that a king moves on a chessboard. A king can move to any cell that's like adjacent by a side or by a diagonal to the cell. So we're asking for, so basically if we were to label each cell that the king, if we were to label each distance that like it would take a king to move, a king can move to all of these squares in 1, and then all of these squares in 2. So it's also saying that the maximum of the distance we move in x and the distance we move in y is less than or equal to 2. That, or the distance a king would take to move on a chessboard would also be 2. So it's any cell that's within 2, yeah. So what it also means is, like, we can think of this square as like kind of a coordinate system. So we have like where we go 2 columns to the left, we go 1 column to the left, 0, 1 column to the right, or 2 columns to the right. Similarly, we can go 2 rows up, 1 row up, we can stay the same, we can go a row down, or we can go 2 rows down. And so we can pick any combination of these points and then just move there. So it's kind of like to traverse all of the squares in this 5x5 square, we can simply iterate one variable from -2 to 2, then iterate another variable from -2 to 2, and then we can go in any place in that square. That's where that kind of comes from if you're seeing my code, because that's the idea I had. So let's see how much I can undo now. Okay. That's fine. So yeah, so how do we do this? There are many ways. Basically, it's a shortest path problem, where each movement to an adjacent cell it costs 0, and each teleportation you do, for example, here, 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 will cost 1. And we're looking for the shortest path from this vertex to this vertex to this vertex. Now, there are many ways we can do this. Constraints are kind of big, and you're given 2 seconds. So it's not that great of an idea to do something like dijkstras, because, let's see, how long did my solution take, actually? Let's look at my submissions. Okay, my submission took 151 milliseconds, which I guess is fine. I guess it wouldn't be that terrible to have another log factor, but I don't know how constants would work, but there's a better way to do it. And it's called 0-1 BFS. This is a useful topic. Like, I remember once there was I think it was a div1c, where basically if you knew this, you would just win, because the problem was just 0-1 BFS. And a lot of people tried dijkstras, and they ended up either getting hacked or failing system tests. So it's kind of useful to know this, because sometimes that extra log factor that something like dijkstra will add does matter. And I remember I used 0-1 BFS in that contest, and I did not fail system tests, so it worked out. So what is 0-1 BFS? 0-1 BFS, let's say you have some graph. And this is, we can again model this as a graph, so this is basically equivalent. Let's say we have some graph, directed or undirected edges, it doesn't matter. Let's just say it's directed. And each edge has a weight, either it's 0 or it's 1. We can only do 0-1 BFS on graphs that look like this. And technically it doesn't have to be 1, it has to be like either 0, it can be either 0 or k. Like for example, those can be the 2 types of weights we have. It doesn't necessarily have to be 1. I'll explain why later. So if you understand BFS, the reason it finds the shortest path to each node, so normal BFS works where every edge has cost 1. That is, it's an unweighted graph. So The reason BFS works is because by the time it visits a vertex, every vertex it visits is like the optimal path. And we can prove this kind of like, it's kind of inductively, but not really. Like say we start at a vertex, right? Then, let me draw a few more edges. Okay, this is ugly. This is very ugly. Let's just do that. And I guess like this. So we start here. And this edge, this distance is 0. This is kind of a bad example. Alright, so now we go out to all edges that go out from this vertex, specifically this vertex, right? Now, if there was, let's say 1, so if there was a better path that was shorter than 1, then like, we would essentially find it earlier. Because the way it works is, first we visit all vertices that are at distance 0 away. Alright, let's just mark all these first. So these are 2 away, these are 3 away, and this is at 4 away, I think. Yeah. So the way BFS works is, first we visit all vertices that are at distance 0. Then we visit all vertices that are at distance 1, ... Then we visit all vertices that are at distance 2, ... Then at distance 3, ... And at distance 4, and then we continue on. So we visit all vertices at a certain distance before we move on to the next one. That's how DFS works, and that's why it's optimal. The proof for that, I'm not exactly sure how it works. It's kind of intuitive because, like, first of all, obviously we're going to visit all zeros first because we just stick them in the queue. Then we visit all ones, right? So if there's some vertex where the distance to them is 1 and we don't visit it, then like because we're using a queue, the distance would have to not be 1. Because if we have some like detached vertex and this, yeah, this is distance 0, this is distance 1, and let me think about this for a second. So we start, if it's distance 0, we put it in the queue initially. Then as soon as we put this in the queue, we'll put this in the queue with all the other ones, just like we did with the other ones from that. So for every 0, we're going to put all their neighbors in the queue. So if this is a 1, then it has to be a neighbor of a 0. And if it's not a 1, then it's not a neighbor of a 0. And if we have some 1 that's like, that we don't visit with the rest of these, then it can't have been a neighbor of a 0, and it can't be 1 therefore. So now we visit all 1s at once. Then we put all the neighbors of 1s into the queue. And therefore, we're going to visit all the 1s, and then after we visit all the 1s, we'll visit all the 2s. And again, so if there was a 2 that we don't visit with the rest of them, say we visit it earlier than the rest of the 2s, then it must have been a neighbor of a 0 because all of these 1s are just a neighbor of 0s. And if it's a neighbor of 0, then it's not a 2. And if there's some 2 that we don't visit, then it can't be a neighbor of a 1 because we have all the neighbors of all 1s in a queue. And so this goes on, and we just extend it out to infinity. So it's a bit like induction, a tiny bit, but not, I don't know, it's not formally induction. If you don't know what induction is, don't worry. It's just that it's basically the principle that I applied. We prove it's true for some n, and then we use that to prove it's true for n plus 1. And then, yeah. So, anyway, this is normal BFS. This is not 0-1 BFS. So 0-1 BFS works if all edges are either weighted 0 or k. In this case, k equals 1 because it takes 1 unit of magic. to do a teleportation. So let's say this is 1, this is 0, this is 1, this is 1, this is 0. This is not the graph we're going to create here, it's just a random graph, or arbitrary graph. And now what do? So in this case we can't just use a queue, because we have to maintain the same property. The first we visit all zeros, then we visit all ones, then we visit all twos, then we visit all threes, and so on. So what we're going to do instead is we're going to use a deck. And a deck, it's a thing in C++, but what it means is it's a double-ended queue. That is, it allows you to both put an element at the front and at the back. So it's like a stack and a queue in one. And the reason we use this is because the process of 0-1-BFS is as follows. When we're out of our text, let's say here. For all edges of distance 0, we push it to the front in the stack part. And otherwise, for all edges of distance 1, we push it to the back in the queue part. I'll let that sink in. And now, think about why we're doing this. Again, the whole point is that we visit zeros first, and then we visit ones first, and so on. So right now, let's say we're in the process of visiting all twos, right? Now, either we have an edge, and if it's a 0, then it's going to go out to another 2, otherwise it's going to go out to another 3. So if it goes out to another 2, we want to visit it with the rest of the 2s. So we might as well visit it next because it's just another 2, so it's harmless. Otherwise it goes out to a 3. So we want to make sure that we visit this after we visit all 2s, so we put it at the end, and once we're done with all these 2s, then we'll move on to the 3s. So you can think about why that works, and it does. But the point is that like we still maintain the property that we visit all vertices of a certain distance before we visit the vertices of the next distance. And you can actually extend this to any sort of number of edges. Like let's say, for example, you're visiting all 2s. Then you have 3 types of edges. Those that have weight 0, those that have weight 1, and those that have weight 2. Then what you can do is you can keep like buckets. And this bucket, this is the 2 bucket, and it stores all vertices with distance 2. Then you have a 3 bucket, then you have a 4 bucket. Then, like, you'll just put all the vertices of distance 0 in this bucket. And then you'll put all the vertices of distance 1 in this bucket, and then all vertices in distance 2 in this bucket. Then you'll make sure that you visit everything in the 2 bucket first. Then you'll move on to the 3 bucket. And when you have a 3 bucket, now you have to make a 5 bucket to store for the ones that are, to account for the ones that are 2 away from 3. I don't remember what this is called. It's like a fancy modification of dijkstra, where it works very well for small weighted edges. It also doesn't have a log factor, which is nice. And it's basically like a generalization of 0-1-BFS. 0-1-BFS uses a stack and a queue in conjunction because it's basically like simulating the 2 buckets and the 3 buckets. Anyway, that was a long tangent. But that's the idea of 0-1-BFS. So basically, now that we've explained that, like every time we move to an adjacent one, it's an edge with weight 0. And every time we teleport, it's an edge with weight 1. So you just need to like implement the grid part and just do the 0-1-BFS. Yeah, that's how it works. That's the entire solution. So yeah, in the timestamps, I'm gonna cut that part out. You can hear about it if you want, but if you just want the solution to D, I will let you have that. I'm sorry. Anyway, so for E, you actually have another grid, which is kind of weird. Let's use this one. We'll use the second one from the input. So you're given a grid. However, this time you can't store the grid in memory because like it's an H by W grid, and H and W are less than or equal to 3 times 10 to the 5th, which means H times W is less than or equal to 9 times 10 to the 10th, which is a lot of memory, more than my subscribers are ever going to give me. So if you don't understand now, watch the last video, or watch the previous video. Anyway, so let's see. And in this grid, there are M targets. Let's see. What do we want to call the targets? Let's call them apples. Why not? So we'll draw them in red, and we have a bunch of apples on a grid. So let's say first one's at row 3, column 3. The second is at row 3, column 1. The third is at row 1, column 1. And the fourth is at row 1, column 2. So in one square, let's say we can place an orange. And then this orange is going to blow up. And it's going to destroy everything in the same column, or in the same row, or in the same column. Okay. And yeah. So there are certain constraints here. So the number of apples is also at most 3 times 10 to the 5th. And that's important because, like, first of all, if it wasn't, we couldn't even read the input. So that's important that it is. And yeah. So we want to basically find, of all the places where we can put an orange that's going to blow up, what's the most amount of apples that we can destroy? And how do we do this? So let's say that each row has AI amount of apples. So this is A1 for row 1, A2 for row 2. Yeah, we're actually using one indexing. It's crazy. So A1 is equal to 2, A2 is equal to 0, and A3 is equal to 2. Right? So the important part of my solution is that the sum of all AI is obviously equal to the number of apples we have, which is just k. Like the number of total input apples we have, which is k. So let's fix the row where we put the orange. Like, let's say we're going to put the orange on this row. Right, so by default, we get all of the apples on this row. But let's say we put the orange on this row, right? So we get nothing. So now we want to figure out which column it's best to put it in. So for example, we have 2 apples in this column, 1 apple in this column, and 1 apple in this column. Wait, I'm going to make those red. 2, 1, 1. Red for apples, right? So we want to take the column that gives us the most number of apples. So we would, in this case, take this one. But let's say we put an orange where there actually are apples, right? Now these change. Now we have 1 apple here, 0 apples here, and 1 apple here. And so we can take either of these. We don't actually have to print where we put the orange. We just need to print the maximum number of apples we can kill. So what do we do here? Let's say we've already fixed the... First of all, let's say we have these counts already pre-computed, which we can do. Since these are at most 3 times 10 to the 5th, the number of columns, we can just make a big array, initialize them all to zeros, and then like put the, for each apple, just increase the count in its column. Okay, so now we're going to put an orange here, right? So let's just say for each apple in this row, we're going to decrease its count, the count of its column by 1. Then we just take the maximum over all columns we have. There are many ways you can do this. I think the most convenient is actually a segment tree because it's just point update, decrease by 1, then it's a single range maximum query. However, this isn't necessary. You can do other things. Like, for example, what I did was I stored a multiset of all number of apples in each column. So for example, here we remove this. So now we remove 1. So now we rebuild the multiset, or we remove the 2 from the multiset and we insert a 1 in. Then we go back here, and then we So now this changes to 0. So we remove a 1 from the multiset, and now we change that to 0. And so C++ is cool, and it has multisets that let you get the maximum element. So after you update the multiset to account for the changes in apples, you just take the maximum. And then the answer for a row is the maximum of the multiset plus the number of apples that are already in that row. And this way you won't overcount because you count the apples in each row once and the apples in each column, and the apples in the column you take once. And even if like you do something here where, oh right, no, it just won't overcount. Never mind. Ignore that thought, it's useless. Yeah, so then once we go back, once we move to a different row, well, we can put these apples back on this row. So we change this back to 2, delete the 1, and stick a 2 back in. And then same thing here, we change this back to 1, delete the 0 here, and stick a 1 back in. And we just do this for all rows. We decrease the counts of all of the apples in the row, or we decrease the counts of all of the columns, update the multiset, then increase them back and re-update the multiset. It's probably convenient to make a function to update like a count instead of just implementing each time, because otherwise there'll be some copy pasting involved since you need to both delete and insert. So that's just convenience for implementation. It's not exactly necessary. What I did was I did this. Let me see. Yes, I basically made a function that says change this position by this value, and then you erase it from the multiset, change the value, and then put it back in. And then here I would just, so initially you would increase the count by 1 each time, and first put everything in the multiset. Then here, for everything in the same row, decrease it by 1, take the maximum, then increase them all by 1 again. And that's the implementation. It's rather smooth, actually. Now let's see. Okay, so you saw I spent, what was it, 70 minutes thinking on F, and I still have no idea how to do it. So I'm not even going to attempt to describe a solution because I have nothing that will work, I don't think. Maybe the solution I was thinking of is actually right, but I don't know how to implement it either. So yeah, I'm not going to mislead you with this. So I don't know how to do it. We'll leave F for, I don't know, other people maybe, the editorial, which doesn't exist yet. Anyway, let's see how we did. So we finished in rank 31 or 51. What was our rating change? Did we get another 2400? Well, we did. Okay. So right now, in terms of doing ABCs, we have the best possible rating we can get, I think. Because the maximum rating, like the maximum quote-unquote performance you can get is 2400. And yeah, we're right up there with this guy who also keeps getting 2400. Except he wins both of them, which is crazy. Okay, yeah, he got 29th in AGC. What did he do? That is crazy. That is very crazy. Was this one rated? I wonder why that was unrated for him. Anyway, yeah, that is crazy. So that's basically it. That's all the solutions I can do, A to E. Hope you enjoyed watching me struggle on F, I guess. And yeah, that is it. See you guys.